Hello and welcome to our second lecture on mechanical equilibrium. This is Chapter 2 in Hewitt's Conceptual Physics textbook. Now, in our first exciting episode, we learned that a force is required to change the state of motion of an object. A force is any kind of push or pull, and a force is required to make an object change its motion. They're also required to change an object's shape or size. The combination of all forces acting on an object is called the net force. So you can have multiple forces acting on the same thing at the same time. You have to add them all up, and the overall net force determines the type of change that occurs. We can represent forces with vectors, arrows drawn on diagrams, such as the one shown here, with 4 forces shown on an airplane. If the net force on an object is equal to 0, no physical changes are occurring to that object. Such a state is known as mechanical equilibrium. Mathematically, we can show that the sum of forces equals 0 is called the mechanical equilibrium rule and represents a state in which no physical change is occurring. In this case, the book remains stationary. But there's actually 2 types or categories of mechanical equilibrium. The first is the one just shown, where objects are at rest. We're going to call that static equilibrium. But objects that are moving at a constant speed in a straight line are also at equilibrium. We'll just give it a different term. Let's go back and again just formally define on your study guide that the state of rest when an object is not moving is called static equilibrium. The sum of the forces on the book shown in the picture here adds up to 0. So static equilibrium is a subcategory of mechanical equilibrium. But another category is dynamic equilibrium. Any object moving at a constant speed in a straight line. Later on, we're going to define that as having a constant velocity. That's also a state of equilibrium. Once an object is in motion, and if there is no net force to change that state of motion, then that object is in dynamic equilibrium. It doesn't mean that no forces are at work. It means if you add the forces up, they add up to 0. And so the object doesn't change whatever motion it has currently. Now, if there's only one force acting on an object, it cannot be in equilibrium. The only way to be in equilibrium is if you have 2 or more forces that add up to 0. Shown here is a diagram of the planetary system that we call our solar system, and the planets are going around the sun because gravity is pulling on them. You'll notice the planets are not going in a straight line. Since they're not going in a straight line, they must not be at equilibrium. It's possible, if you were in outer space, that an object could be moving with no force at all. Maybe a force got it started moving, but then it would move constantly in a straight line with no force at all. But here on the Earth, there's always going to be forces, more than one force, acting on an object at any given time. Only if 2 or more forces combine to 0 can that object be in equilibrium. Here's a man pushing a desk or a chair across the room. So the man is applying a force to the chair. Now all that's shown in this diagram currently is one force, the man pushing. But in real life, there is an opposite force at work. We call it friction. Friction is any kind of contact force between objects, especially those that are sliding or tending to slide against one another. So if this man is pushing the desk and the desk is speeding up, then the net force is greater than 0 the man is pushing with a greater force than friction is pushing back with. But if he's pushing at a constant speed, and yet he's applying a force, there must be an equal and oppositely directed force, known as friction, to keep that desk moving at a constant, unchanging speed in a straight line. In other words, if the chair is moving steadily at a constant speed without any change in its motion, it is in dynamic equilibrium. The sum of the forces acting on the desk must be zero. Friction is equal in magnitude or size, but opposite in direction of the man's pushing force. Let's stop and think for a moment. Here's an airplane flying horizontally at a constant speed in a straight line. Its state of motion is unchanging. In other words, it is at equilibrium. Two horizontal forces are acting on the plane. One is the thrust of the engine that pulls it forward. The other is the force of air resistance, or air friction, that acts in the opposite direction. Which of these forces is greater? Many of you have experience flying on an airplane, but you can also take a more mundane object like an automobile and apply the same question. You know that if you're in your car and there is a motor running, that there is a force propelling you forward. But if you are going at a constant speed in a straight line, then there must be a counteracting equal and opposite frictional force. In other words, neither air resistance or thrust is greater. They have the same strength. If we call the thrust positive and the resistance negative, if you add those two values together, they will add up to zero. The plane is at equilibrium, and the two forces, the sum of the forces acting on the airplane is zero. So having a zero force doesn't mean you aren't moving. It means you aren't changing your motion. It's very important to keep that in mind. The sum of two or more vectors is called the resultant. We saw this in an earlier slide in the first video for mechanical equilibrium. If you take two forces acting on an object and add them together, you get a resultant. When the forces are parallel, adding them together is relatively simple. If they're in the same direction, they add together. If they're in opposite directions, they also add together, but you call one of them negative. So in effect, one of them is subtracted from the other. Here's little Nellie hanging from a rope. If she weighs 300 newtons, that's the force of gravity acting downward. The rope must be applying a tension of 300 newtons upwards. It can't be greater or less, or else little Nellie would be changing her motion. If she is stationary, then equal and opposite forces are at work. Now, instead of a single rope, what if little Nell had two ropes holding her up? What is the tension on these ropes in this situation? Well, she's still stationary, so there must be a 300 Newton force acting upward, just like in situation A that we just saw. In this case, the two forces in the rope must add together to give you that 300 Newton upward resultant. So the tension in each rope, if they're parallel, must be 1/2 of her weight, 150 newtons. That way, there will be a 300 Newton total upwards to add to a 300 Newton total downward to give you a sum of zero. Now, what if the two forces are not parallel to one another? What if they're at right angles, such as shown by the vectors in this slide? Your book describes finding a result or the resultant of two non-parallel vectors with the parallelogram rule. Basically, what you do is you take both of these vectors and recopy them tail to tip like this. Let's move the green arrow over so that its tail is now on the tip of the red arrow, the bottom arrow. Let's take the bottom and move it upwards so that its tail is at the top of the green arrow now. And basically the resultant goes from the place labeled O here for origin, where the two vectors were drawn together to begin with, and you draw the resultant to where the two tips are now touching. So there will be a diagonal like this. So the blue line shown on the screen is called the resultant, and it's often labeled with a capital R. Just a little side note, the resultant, if you calculate how long it is and compare it to how long the original vectors were, you can get an idea of the size of the net force if you draw everything to scale. Well, if the left and the right arrows, I should say the up arrow and the right arrow here, if they're at right angles and they're equal in size to begin with, then the parallelogram is going to be a square. The resultant or diagonal of any square is going to be 1.414 times any of the sides. So that's just a special case. If both vectors are the same size in magnitude, but at right angles, then you just take either one of those sides, multiply by 1.414, the square root of 2 in other words, and you will get the size, the magnitude of the resultant. And it will be a 45-degree angle compared to where the two vectors were before. But that's a special case. A lot of times our vectors are not at nice right angles, such as the one shown here. Little Nell is suspended. She's at rest. She's not moving. This time the two ropes are not vertical. They're not parallel to each other. So what is the tension in the rope in this case? Well, we could apply the parallelogram rule. Let's go back and consider this first case that we were looking at. She was hanging by two ropes, but they were parallel to each other. And we said that the resultant, the upward tension force, must be the same as in the original case where she was hanging by one rope. In other words, the two vectors and the two ropes shown in B must add together to equal 300 newtons up. You can use what's called the tail to tip method to show this to yourself. If everything's drawn to scale, if you take those two vectors, let me change their color and move them over one at a time. There goes one vector, there goes the other, and we'll put the tail of it on the tip of the other vector, and the resultant now is the total length of those two combined, and you see that the equals 300 Newton vector as we predicted it would. So if you add those two vectors together, you get a 300 Newton upward force. Well, in this case, there is nowhere for an upward force to be. There's no rope right above her hand. Instead, the tension is in two ropes that go side to side, but they have to add up to that blue resultant line. There's got to be a 300 Newton straight up resultant. Otherwise, she would be moving. She would be changing her motion. If you look at it in a parallelogram, you can see how the resultant was obtained. If you take the purple vector and move it up tail to tip, the green vector, move it up tail to tip, then the resultant is from tail of the original two vectors to the tip of where they come together now, and we can see that that resultant is there even though there's no rope there to support it. It is a combination of two forces at angles to each other. Now this is kind of complicated at this point, and I actually should have told you that there are no notes for this section. I just want you to watch from this point on, and then we'll have some practice problems for you. Just like in the example before, when she had two ropes but they were directed upward, the resultant has to add up to 300 newtons. If the two vectors are not parallel, they still have to add up so that it cancels out her weight, otherwise there would be motion. Let's take Nellie out of the picture and ask this question. If she's suspended by the two non-parallel ropes, is the tension in those ropes greater than, equal to, or less than the two non-parallel ropes? Well, if we stand those two vectors straight up and then move them over, I think it's pretty clear, if everything was drawn to scale, that the tension in each diagonal rope is more than half of little Nellie's weight. In other words, it's going to be greater than 150 newtons in the two diagonal ropes. So there's a lesson to be learned there. As the angle between the two ropes increases, we're spreading the ropes out end to end. The resultant still has to add up to 300 newtons, but it takes a longer vector on the rope sides to get to that same 300 newton upward vector. In other words, the tension on the rope is increasing. You could take a rope and hang it straight down, and maybe you could sit on it. You could put your swing on it and swing back and forth. You could take that same rope, put it side to side, and then try to hang from it, and it might break. It has a lot more tension in the side to side than it did in the straight up and down position. Here's a thinking question. We have two swings on this playground set. If the children are of equal weight, which of these would be more likely to break if the children started to swing? Well, the little boy in purple on the left, the vectors are going straight up. The little girl on the right, her vectors are not parallel. The tension in those ropes are going to be greater, and so she's more likely to fall than the little boy. What if you had something really tightly strung, like a guitar string, and you hung a weight from it, and then decided to tighten it up even more? Would it be possible to tighten it up so tight that it still went straight across, just like it did when there was nothing hanging from that string? No, that's not possible. If anything hangs from the middle of a string, there has to be an upward resultant to counterbalance the downward weight. Otherwise, that weight's going to be moving. The only way that something can be stationary is if the sum of the forces adds up to 0. So there has to be an upward directed force to counter the 10 Newton downward force. That means there has to be some angle in the string. Cannot go straight across. Consider one last situation. Instead of hanging right in the center, what if little Nellie moved over? Now, the two supporting ropes are at different angles. What's the tension like in the two ropes at this point? Well, again, you could use a parallelogram method. If you draw some parallel vectors, but move them over tail to tip, so that the resultant is at the place where the two dashed vectors come together, then you can see that those two dashed vectors are not the same size. That means the tension in the rope is not the same. In fact, the one on the right is going to be much greater than the one on the left in that case. Now, all this vector drawing, this is traditional physics, and they do a lot of this in a traditional physics class. We're going to try to keep it to a minimum because I don't think it's really all that important for your understanding of a lot of other concepts that are equally important later on. And so I don't want to spend a ton of time doing vectors, but we are going to spend a little bit of time doing it. So please review the book and try as best as you can if you, to learn how to do this vector method. But let me recommend that instead of using the parallelogram method, you just take the vector, take either one of the vectors, and just move it tail to tip. The resultant then goes from the origin to where the last arrow's tip lies. Okay, in summary, forces are pushes or pulls. They attempt to change an object's motion or its shape or size. We tend to focus on motion. Any given object might have more than one force acting on it at any given time, and you have to add those forces together to get what's called the net force. If the forces acting on an object add up to 0, if the net force is 0, then the object motion does not change. But that could mean one of two things. It either remains stationary, which we call static equilibrium, or it remains in motion in a straight line at a constant speed, which we call dynamic equilibrium. We can represent forces with arrows and drawings. Those arrows or vectors can be added together if you draw them to scale and draw their angles accurately. The net force then is represented by an arrow drawn from the origin to the last arrow tip. That resultant, if you draw it to scale, will not only represent the magnitude of the net force, but also its direction. Now, the textbook describes using a parallelogram method to find the resultant, but if you just take any one of the vectors and add its tail to the tip of the next one, you can actually use multiple vectors that way instead of just two. So we'll show you some examples of using tail-tip vector addition in future videos. For the time being, please flip your study guide over, and there are some questions to be answered there. And I'm sure that you'll also be receiving some worksheets to complement these videos. Please rewatch the videos at your pleasure. They're available on YouTube. And if you have any questions, come and ask Dr. Kemp for help. Thanks for your attention.